All right, hello, good afternoon. So, let's see, this will be the 14th video in this lecture series. Now, you may notice if you've been watching through some of these that normally I say good morning instead of good afternoon. Well, the reason for that is that in this case, I am recording a makeup video. Normally I have this course on Monday, Wednesday, and Friday mornings for the semester. But today is Friday afternoon, and I'm recording a session in lieu of Monday, which would be on President's Day. Anyway, so let's begin. All right, so I have a few learning objectives for today's lesson. First, I wish to derive the general form of the mass flow equation. Second, I wish to apply mass balance for incompressible flow applications. And three, I wish to explain the difference between mass and volumetric flow rates. So we're going to continue with some of our discussions for continuity and transport theorem, control volumes, etc., looking at some of the topics from chapter 5 of the Munson text. All right, so let us discuss continuity. Let us discuss continuity of mass, volume, etc. So a conservation of mass and a continuity equation. / continuity equation. All right, so let us look at the continuity equation. And first we'll sort of build up to it and discuss simply continuity. Well, continuity and also laminar flow. So the continuity equation, and we'll see this later on. We have seen this a bit already, but in comparison to earlier material, rather than looking at fluids at rest, we are of course looking at fluids in motion. And primarily we are looking at materials that are in laminar flow. So what is laminar flow? Essentially, laminar flow is your standard nice flow that balances the same that behaves the same way over time. So when we say laminar flow, we're talking about a steady flow. It doesn't have to be in a straight line, but it does have to be a steady state, non-turbulent flow. And later on, when we actually get to things like Reynolds numbers, etc., we will learn how to actually define mathematically what laminar flow is. But for now, just think that laminar flow is steady state flow, steady state non-turbulent flow. That is what we're looking at. So we will not have any air pockets or bubbles or anything that would interfere with our simple equations of continuity. No voids, pockets, changes of density, etc. Now you may have something that changes density, but if you were going to have laminar flow with it, it would have to be a smooth change in density. So if you want to think of the exact opposite of laminar flow, instead imagine, say, a waterfall or a turbulent whitewater rapids. Those are sort of the exact opposite of laminar flow. So, and it's also completely predictable. That is another key for laminar flow. It's completely predictable. What do I mean by completely predictable? Well, it can be very complex. It doesn't mean that I can mathematically predict something. But in other words, if I have a flow field, an object released into the same place in a flow field will travel on the same path every time, or the same type of object at least, or the same object preferably. You could just do it repeatedly. Into a flow field repeatedly will follow the same path repeatedly. Repeatedly will follow the same path repeatedly. So, for example, if I have a flow field, let me draw this not in black. Let me use light blue or something. Nice waterish color. So say I had a flow field, have some streamlines here. Oh, and let's see, I can make it behave however I want. To this application, it really won't be important. But anyway, we see that we have very nice continuous streamlines. And so if I release an object here, say I released a small circular piece of wood, a small ball of wood here, well, it's just going to happily follow the streamline, and then it will end up over here. I can pick it up out of the water here, walk it back along the shore, release it here, and it'll go right back along the same path. And I can do this 100 times, again and again and again, and it will never follow some very random or unpredictable path. If the fluid is not laminar, or especially if it's turbulent, it will not exhibit that characteristic. Instead, it will follow very unpredictable paths. And you can analyze turbulent flow. You can analyze turbulent flow, but you cannot actually predict exactly how it will behave. The analysis you do is, say, finite element models of turbulent flow. Those are really just to sort of get the idea of the general behavior of the system. You're not actually trying to make predictions for how something in particular will flow in most cases. Okay, so let us consider another limitation of this, or another application of this. So we're talking about steady state flow. So let me also go into another assumption behind the conservation of mass or continuity equation. And this is, of course, steady state flow. We've discussed this a bit before. Let us see this. Steady state flow. So if I show another one of my famous pipe constrictions, I would see something like this. I can draw this out. Actually, let me draw maybe the cross section, and then I'll draw the actual cross sections in blue with a circle or something. Something like this here. And then I have a cross section like this here. So how does basically I'm looking at how steady state flow interacts with continuity. So I have a flow here, velocity v1 and velocity v2. And I'm going to call this one A1 and A2. Fairly simple, straightforward. A1, A2. And this is the same again, and we've discussed this before. This is the same principle at work behind a garden hose sprayer. Really any application where the velocity of the fluid increases rapidly. And I'm going to define my control volume as something like this. I could define it as along the walls of my container, but the nice thing about doing a nice box like this, it makes if we were to analyze this very mathematically with a surface integral, it would make the analysis much easier. It would of course make the analysis much easier. Okay. So V1 and V2, and again with steady state, what we're talking about when we say steady state is we're considering something that does not change with time. So that's something to note. Steady state again means not changing with time. So what is not changing with time? Well, if a system is in steady state, what is not changing with time is the contents of our control volume. In other words, our rate of change of energy, our rate of change of mass, our rate of change of volume, or our rate of change of momentum, all of these are equal to 0 within the control volume. Well, actually, I probably shouldn't say flow rate. That's probably the wrong way to say that. I'd probably say something like well, maybe you could. But anyway, I should probably just say they're all constant within the control volume. So because usually when we say flow rate, m dot, we're talking about the amount that flows past a control surface. So I have to be very careful with that. We will still have flow, we just will not have the overall amount will not change inside the control volume. So M, P, V, E, all constant within the control volume. So if you remember the case previously where we looked at if you remember the problem from last time, where we looked at the cart that was filling with water, that would not be a steady state system. Okay, so again, here, just to label, we have a variable diameter pipe with a fixed volume. With fixed volume. And then the question becomes, again, of course, what is the relationship between V1 and V2? Now, I have mentioned this before, but we can actually see from the continuity equation that, and we can actually build this from the continuity equation. The continuity equation says that momentum in equals momentum out. That P dot in equals P dot out. Or rho, or simply rho AV equals rho AV for 1 and 2. And then, of course, if the flow is incompressible, then the rho 1 will be equal to the rho 2. Rho 1 equals rho 2, and this leads us to the equation that we've seen previously, where A1V1 equals A2V2. Very simple. Okay, so let's ask a few more questions about this. And again, we know that large area will equal small speed, and the opposite. Large area equals small speed, and the corollary, small area equals large speed. Momentum needs to be conserved. And actually, this would sort of, actually, now that I think about that, it's probably not, that actually isn't momentum. Sorry about that. I really screwed that one up. That is simply m dot in and m dot out. Yeah, this is not actually a momentum relationship. I screwed the pooch on that one. Sorry about that. This is m dot in equals m dot out. Let's see. So yes, m dot in, because we take, this is going to be a volume, and this is going to be a volume per second, area times, so this is meters squared. For example, a meter squared times meters per second, that'll be a volumetric flow rate, times the density will make that a mass flow rate. So sorry about that, that was not momentum. So a small area equals a large speed, or a large area equals a small speed. Really straightforward. And another way to think about this, e.g., if A doubles, then V has to compensate. V has to absorb that increase. Thus V halves. So if area doubles, then to keep this constant, then area has to be constant. Oh, sorry, if V doubles, then if the area doubles, then the velocity has to go in half in order to keep the system in balance. And the question is, though, why? Why does this have to happen? Well, it comes down to a delta T relationship. And let us look at what happens in delta T. So in delta T, what happens then? Well, let's look at it on the next slide. in a time delta t, what happens in the pipe? Well, let's look at this in a little more detail. So we have this here, and this here. And let me show area 1 and 2 again. I'm going to show them in 2 different colors. And both, I'm going to draw this, the area 1 and area 2 circles twice. And I'm going to assume that both of these circles are well in the range that we're still at the constant diameter sections of the pipe. Here and here. So let's go back to this. We have V1 and A1, and we have V2 and A2. A2 and V2. And then what is the length of each path here? Well, the length of this path is going to be V1 delta t, and the length of this path, of course, is going to be V2 delta t. V2 delta t. So again, this is based on the relationship that, if I want to make a little note here, the way I got those dimensions, recall that V times t is equal to distance. And so, this is all going to come down to the conservation of mass. This is all about conservation of mass. So, in 1 second, or in 1 delta t, this volume is going to have, this is the amount of volume that enters in on one end. So the amount of volume that enters in on one end, we have volume coming in. Let me show you this. In and out. Volume in is going to be V1 delta t, that's the height of the cylinder, times A1. And volume out is going to be V2 delta t times A2. And then, because again, these are just volumes of cylinders, all I'm doing here is taking the volume of a cylinder. The cylinder has, there's a cylinder of fluid here that has a length or a height of V2 delta t and a prismatic area of A2, and the opposite here. Then, if I want to find the mass, if I want to say mass, well, mass in is going to be this just times rho. So rho V1 delta t A1 is going to be equal to, and of course these have to be equal, rho V2 delta t A2. And for incompressible fluid, if I were to write these out, or sorry, if I were to cancel a few things out, if it's incompressible, the rho is going to be equal, and the delta t's are the same. And this is again how we get our V1 A1 equal V2 A2. All of this comes from the very simple identity of conservation of mass. There must be as much mass flowing into this restriction as flowing out. Mass cannot be created or destroyed because we're not doing any kind of really strange nuclear reactions or anything. So there must be as much mass coming into our control volume as leaving our control volume. So m dot 1 equals m dot 2. They have to be the same, and that is really the entire basis of our control volume or our continuity equations. All right, and then if I want to look at this in a more general form, we can see this in equation 5.16 of the text. And this is going to be our continuity in more general form. And so I have d dt, or the partial with respect to t, across the control volume of rho dv. Plus the integral across the control surface of rho w dot n dA, and this is equal to 0. So this is the general form of continuity equation, Previously, I was looking at a specific application of it. Continuity, oh, well, that is not correct. Let's say general form of continuity equation. You can tell it's Friday. General form of continuity equation. Okay, so the question then becomes, what is W? I thought we were dealing with velocity and such. Well, W is the relative velocity of our control volume to our fluid. Relative velocity between control volume and fluid flow. Control volume, if I can manage to write the word between properly, between control volume and fluid flow, between our control volume and fluid flow. However, one of these terms is meant to take into account the deforming of the fluid, deforming of the control volume. So really, the way to interpret this is this term right here talks about the change in the control volume itself. It is basically a measurement of the change in the control volume. So if the control volume is deforming, then this term will not be equal to 0. And this represents the mass flowing in and flowing out across a control surface. But if control volume is, so basically what we can say here is that if control volume, so now I'm going to look at it, so again, this is the general case, and let's consider two specific cases. If control volume, and actually let me put a big red box around this to show how important this equation is. I like putting big red boxes around important things. Okay, so then if control volume does not deform, if the control volume does not deform, well then we can have the relationship, or we can, not really the relationship, we can just cancel out one of these terms. The first term will disappear. The partial of t of the control volume, rho dV, of the integral across the control volume of rho dV, will simply be equal to 0. Then, if control volume is stationary, that does not mean that this term is equal to 0. However, it does mean that W will simply be equal to the velocity of the fluid flow. And in that case, we would say, we would reduce this to a more limited case, and we would say, okay, the integral across the control surface of rho v dot n, dA, and this is for a stationary, non-deforming control volume. So this is a particular case that we may want to consider. This is for a stationary, and this would actually be equal to 0 for a stationary, non-deforming control volume. Non-deforming control volume. Non-deforming control volume. All right, so now let's see how we might actually use this equation. Here. So let us consider the previous case. So let me write out this special case of the general continuity equation. And the integral across the control surface of rho v dot n v dot n dA equals 0. So this is our equation that we're going to be using. And then let us use the case above. In previous case of the pipe restriction, well, the integral across the control surface of rho v dot n dA is going to be equal to negative v1 a1 times rho 1 plus v2 a2 rho 2. Basically what this is saying is if I make a note on a V is going to, the reason we're doing this dot product is that we're looking for the V normal to the control surface. So here, and actually I should just say V is normal to the control surface. So, we're looking for the V normal to the control surface. That is why we're doing this dot product here. So here, V is normal to the control surface. That's the purpose of the dot product. So we're looking for the component of V normal to the control surface. So if you remember from your math courses, the normal vector is going to be perpendicular to the surface. This is your normal vector. And we're looking for the V here. That's why we're dotting it into the N here. We're looking for this V here. And so if we instead have a velocity, if this is the control surface, this is the control surface, if instead the normal vector is, if the velocity is off at an angle from the normal vector of the control surface, we want only the component that is that is perpendicular to the control surface. So if we had a V here at a theta, well then we would not want the entire V, we would only want V cosine theta, which is why we do the dot product in the formula. Now in this particular example, V is already in line with the normal vector of the control surface, so we don't have to worry about that. But it will become important later on. So if I want to use this integral again, we have this, and this has to be equal to 0. And so again, from that we can get our relationship v1 a1 rho 1 v a1 v1 is equal to rho 2 a2 v2. And this is another general form of the equation of continuity for pipe flow. Continuity for pipe flow. All right, so let's see, how are we doing time-wise? Not bad. Okay, we can do a little more. Let's see, so actually, you know what, I think that'll do it for today. I think all I really wanted to do was introduce the basic idea of continuity, or introduce the basic idea of doing a surface integral and how we're going to work with this as we work through some conservation of momentum and other problems later through the semester, or later in this current week, actually. So that'll do it for today, just a short video introducing the ideas of continuity, and that'll do it, and as always, thank you.